Welcome to this explainer. Today, we are tackling an absolute beast of an assessment, the Cambridge AS Level Physics Practical Examination. We are going to completely master the strict, uncompromising rules of experimental methodology by walking together through the entire life cycle of an experiment. I want you to think of this explainer as your ultimate foolproof blueprint for turning that stressful, hands-on lab work into top-tier grades. We are going to build bulletproof arguments with stress-tested evidence, and we're going to do it by thinking exactly like the examiner. Now, you might be wondering, why are we focusing so intensely on this specific paper today? Well, the number on your screen says it all. Exactly 40 marks are up for grabs on paper 3. Think about that for a second. That accounts for almost 1/4 of your entire AS level grade. It is a massive chunk of your final score, and it's divided equally between 2 questions that assess 3 very specific skill areas. Master these rules we're about to cover, and you effectively lock in 1/4 of your grade before you even sit down for your theory papers. It really is that simple, but you have to know the rules of the game. So here is our roadmap for this session. We're going to track the complete life cycle of a physics experiment. We'll start from the very foundation, setting things up, then we'll move into the strict rules for presenting your data, followed by the highly scrutinized rules of graphing. After that, we'll extract the actual physics through analysis, and finally, we'll tackle the hardest part for most students, critically evaluating your own experiment. Okay, let's dive right in. Section 1, the Paper 3 Foundation. This is all about what you do before the clock really starts pressuring you. Before you even touch a single piece of apparatus on your desk, you absolutely must master the concepts of manipulation and measurement. It sounds basic, but under exam pressure, students mix these up all the time. The independent variable is the specific factor that you, the experimenter, control or change. You are the boss of this variable. You decide its value. The dependent variable, on the other hand, is the factor that changes as a direct result. It's the thing you are sitting there waiting to measure. If you mix these up, your entire experiment falls apart before you've even recorded your first data point. Let's look at how this actually plays out in real investigations. We have 3 classic examples here: dropping a bouncing ball, suspending a mass on a spring, and melting ice in water. We are going to use that last one, the melting ice, as our running example throughout this explainer. Notice that if we are investigating the melting of ice in water, the independent variable is the temperature of the water. We control that. We can heat the beaker to 95 degrees or let it sit at 60 degrees or cool it to 15 degrees. We make that choice. The dependent variable, the thing we are hovering over with our stopwatch, waiting to see happen, is the time taken for that ice to melt. Moving on to Section 2, presenting data and observations. This is the part of the exam where the examiner is literally just checking your attention to detail. I need to give you a very quick, very serious warning. A lack of precision here will immediately cost you easy marks. You must fundamentally understand the difference between raw data and calculated data. For raw data, the numbers you read straight off the instrument, your precision must be consistent all the way down your column, and it is entirely dictated by the measuring instrument you are using. If your ruler measures to the millimeter, every single reading needs to reflect that precision. On the other hand, calculated data, like when you use a formula to square a number or you calculate an average, must match the number of significant figures of the measured quantity of least precision. Basically, your calculator is going to give you 8 decimal places. Do not write them all down. You usually give calculated data to the same number of significant figures as your raw data, or just one more. Never let the calculator dictate your precision. This is exactly what examiners want to see. Look at this flawless layout from a resistance experiment. First, notice the column headings. They include both the quantity and the unit, separated by a /. You must have both. You cannot just write I or current. You need I/A for amps. But now, pay very close attention to the middle row under average current. See that value of 0.350 with the little asterisk next to it? You absolutely must not forget to include that trailing 0. Look, mathematically, 0.35 is exactly the same as 0.350, right? But in a physics practical, adding that 0 proves to the examiner that the measurement was taken precisely to the nearest milliamp. If you drop the 0, you drop the mark. Before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's jump into Section 3, the rules of graphing. This is arguably the most highly scrutinized part of Paper 3. You are taking all of that beautiful raw data and transforming it into a visual argument. There are 5 golden rules for plotting graphs, and you need to memorize them. First, draw and label your axes properly. Remember, the independent variable goes on the x-axis, and the dependent goes on the y-axis. Second, choose sensible scales that take up at least half the page. Please, no awkward multiples like increments of 3 or 7. Examiners hate trying to decipher those, and you will make mistakes plotting them. Third, and please listen carefully to this one, plot your points using small saltire crosses. That's an X drawn with a very sharp pencil. Do not draw dots, and definitely do not draw thick, shaded-in blobs. Blobs will literally be penalized by the examiner because they hide the exact coordinate. Fourth, draw a single, clean, best-fit straight line or a smooth curve. And fifth, actively check for any anomalous points that sit way off the trend. Take a look at this perfectly plotted straight line graph. See how crisp those saltire crosses are? They allow the examiner to pinpoint the exact center of your data point. If you use a thick dot, it tends to just disappear into the line of best fit once you draw it, making it totally impossible to verify your accuracy. Also, a really vital tip here. Never artificially force your line of best fit through the origin of 0, 0. A lot of students do this because they think everything starts at 0. Don't do it. If the line naturally intersects the y-axis higher up, let it. There are often very valid, real-world physical reasons why a dependent variable isn't 0, even when the independent variable is 0. You have to let the data dictate the line, not your assumptions. Now, if your data clearly indicates a curve instead of a straight line, the rules are just as strict. A well-drawn, smooth curve is done in one confident single sweep. Hesitation creates a poorly drawn, jerky curve with what we call feathering between the points. You can see the difference on the screen. The bad graph looks like it was drawn by a nervous artist sketching short, hairy lines. Those feathered lines completely ruin your ability to calculate an accurate gradient later on, and they will absolutely cost you marks. Practice drawing curves with confidence.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at @acetheexams_IGCE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, Section 4, Analysis and Conclusions. This is where we extract the actual meaningful physics from those graphs we just so carefully drew.
In almost every single paper 3, you will be asked to find the gradient and the y-intercept in order to determine some unknown physical constants. There is an exact procedural formula for this, and you cannot deviate from it. Step 1. You must choose 2 points directly from your drawn line. Do not, I repeat, do not, just blindly reuse points from your raw results table. Your line of best fit is an average. Your raw data points probably don't sit perfectly on it, and those 2 points you pick, they must be as far apart as possible, separated by at least half the length of your drawn line. Draw a massive triangle to prove it to the examiner. Step 2. Calculate the gradient using the standard formula, the change in y divided by the change in x. Step 3. Use the standard equation of a straight line, y equals mx plus c, to mathematically find your y-intercept. Don't just look at the graph and guess where it crosses.
Let's look at this worked example to see the math in action. Here, the student picked 2 coordinates directly from the line of best fit. 0.06 on the x-axis, 0 on the y, and 0.50 on the x, 1.90 on the y. They calculated the gradient using those points, giving them a value of 4.3. Now, to find the true y-intercept, they didn't just eyeball the edge of the graph paper, they mathematically substituted that calculated gradient of 4.3 along with their first coordinate straight into the formula y equals mx plus c. Solving for c reveals a precise intercept of negative 0.26 amps. Precision right here is absolutely essential because these specific values usually correspond directly to the hidden constants in a physics formula they've given you on the paper.
But let's pause for a moment and be real. All of this beautiful math assumes that our data is flawless. So what happens when measurements aren't perfect? Because let me tell you, in the messy reality of a school physics lab, with fluctuating room temperatures and cheap stopwatches, the data is never perfect. And that brings us to Section 5, Evaluating Your Experiment. This is the final boss of Paper 3. This section is where the truly top-tier A-grade marks are earned. We have to start by mathematically quantifying our doubt using uncertainties. The precision of your instrument gives you your absolute uncertainty. This is usually the smallest scale division on an analog device. For instance, a standard school ruler has millimeter divisions, right? So the absolute uncertainty is plus or minus 1 millimeter.
But to really test whether a hypothesis is valid, you must convert that raw absolute number into a percentage uncertainty. You do this by dividing the absolute uncertainty by your actual recorded measurement and then multiplying that whole thing by 100. This tells you exactly how much your equipment is failing you.
Let's return to our ice cube melting experiment to demonstrate why percentage uncertainty is such a game changer. Imagine a student measures the initial water temperature and then uses a stopwatch to time the ice melting. The absolute uncertainty for the stopwatch might just be a few seconds, let's say 5 seconds, because honestly, it's really hard to judge exactly when that very last tiny sliver of ice finally disappears into the water. Your reaction time isn't perfect. Now, 5 seconds out of a long 85-second melt time gives a percentage uncertainty of about 6%. Not terrible. But for a faster trial, say the water was hotter and the ice melted in just 31 seconds, that same 5-second human judgment error creates a massive 16% percentage uncertainty. Meanwhile, reading the thermometer at the start probably only has a 1 to 2% uncertainty. This proves mathematically that timing the melt is the absolute weakest link in the entire experimental setup.
Once you calculate your uncertainties, the exam paper will ask you to state the limitations of your procedure. Listen to me very carefully. Examiners despise generic complaints. If you just write parallax error or human error on those lines, you'll get 0 marks. You need to identify specific, physical weaknesses in your setup. For our melting ice experiment, here are 4 major acceptable flaws. 1. Taking only 2 sets of readings is entirely insufficient to prove a scientific trend. 2. The ice cubes you pulled out of the freezer might not all be the exact same mass, which completely ruins the fair test. 3. The beaker is open to the room, meaning thermal energy is constantly escaping into the surroundings. And 4, the ice cubes might be partially melting on the warm desk before you even manage to drop them into the water. See the difference? These are specific, physical realities.
Finally, having identified the precise weaknesses, you must prescribe the precise cures. You can't just complain. You have to fix the experiment. Was the weakness not enough readings? The cure is explicitly to take more sets of readings at varying temperatures and plot a graph to confirm the trend. Were the ice cubes different masses? The cure is to use a digital balance to weigh each individual cube before dropping it in. Was heat escaping the open beaker? The cure is to carry out the entire experiment inside an insulated vacuum flask with a lid. Were the ice cubes melting on the desk? The cure is to keep them sealed in a cold refrigerator until the exact, literal second they are required. Match the specific cure to the specific flaw, and you will secure every single mark. And that brings us to our final takeaway for today. As the Cambridge Guide itself states, you will find that you gradually learn the art of critical thinking. Mastering the rigid, heavily structured experimental procedures of Paper 3 isn't just about jumping through hoops to please a grumpy examiner. It is fundamentally about building the critical thinking skills that are absolutely necessary for all your future scientific endeavors. You are learning how to control variables, how to mathematically doubt your own tools, and how to redesign flawed, real-world systems. So the next time you step into the lab, ask yourself, what is the hidden variable here, and how can I measure it better? Students who implement these physics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for physics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.